Hello, everyone. Thank you for staying awake for the last session, which means once the UGM is over, the only thing you remember is my presentation. Just kidding. So I'm Siqing Yi with Alta Planning and Design. We partner with DB ECO North America to deliver this project to VTA, our client, the Valley Transportation Authority in Santa Clara County. And I'm going to present VISSIM simulation of light rail service improvement in Silicon Valley. And by the way, for those who doesn't know DB, they're part of Deutsche Bahn, the German national railway system. Okay, so the question we started for this project was how should transit service in Santa Clara County look over the next 30 years? Currently, they have three lateral lines running on 15-minute headway. And in the future, the vision is to create a customer-centric 10-minute visionary network. What does that mean for VTA? In order to increase ridership, maximize connections, and in the meantime, maintain the same fleet size and crew size and minimize cost, the key is really to increase reliability and reduce travel time along the corridor. So DB's role is to model the entire system in their software, Briato, and develop the conceptual visionary network scenarios for us to test the delay impacts and system capability at some key intersections. Like one is first and Tasman intersection, where we have three lines intersect with each other, and the other one is St. Carlos Wharf, where we have like two lines. So we do have some existing light rail delays as well as traffic congestions at those two locations. That's me visiting my site during a weekend leisure bike trip. Yeah, I'll spend more time talking about the existing conditions because it's not that easy to accurately replicate the current light rail and traffic operations at those intersections. There are a few things I need to tackle. We did the field observation through videos. When we collect turning movement counts, we have at least two angles at each intersection to record all the light rail movements and vehicle queues. And we also have the light rail operation data from DB and from the video observation. And the most difficult part is, of course, the signal timing. And we'll do validation later after we have the existing model. Yeah, so we saw some very interesting light rail behavior at both locations. There are some additional stoppings at the station or before the intersection. One is like, if they arrive ahead of schedule and this is a time station, they'll need to wait at this location more than the standard dwell time of 20 seconds. And we also saw some lower priority trains yield to other routes at mid-block before they even approach to the intersection. We, as well as some trains waiting at the switch, similar to the Muni project, like they're just waiting at the switch before approaching. And for time distribution, because we don't really have 100% on-time performance for those lateral lines, so I apply those deviations between the schedule and the actual arrival time into the PT lines, like here, this customized time distribution. We have the mean deviation of 40 seconds and standard deviation around 20. We got the speed profile for the lateral trains from DB, and at some locations it's very complicated because there are like different kind of curves and also sections where trains running beneath a freeway where we have a slower speed. So I coded all those speed locations in VISSIM according to this diagram. And for PT schedule, we have like 3 different reference systems. One is from the video, we see like arrival time at the intersection. And from the schedule, that's like arrival time at the station. And in VISSIM, the departure time is actually, from where the PT line starts. So I did converge, like between different systems and calculate the offsets. So this is how typically VTA TSP works. After the upstream intersection, we have this advanced detector, and yeah, this whole distance is a travel time between this one to the next one, the check-in zone. And after the downstream intersection, we have this checkout zone. However, for our locations, this is not always the case. So this is part of the timing card I got. As you can see, we have 6 different movements, and each one with its own TSP. So for the eastbound orange line, this one, T3, we don't have a bus detector. And for this Tasman station, like this approach, 5 and 2, the advanced detection is at the station itself because it's too close to the intersection. And for the other direction, it's also at the station, but it's a little bit far away from the intersection, like 800 feet. So next slide, I'm going to show how I coded TSP. By the way, this is also the free operation, and we have like 2 dummy phases for light rail. Like 4 of them are using those 2 dummy phases. And another complication is the LPI. So basically, I did some online search and didn't find a very easy way to code LPI. Instead, there's like a way workaround to code this like overlap signal group with delayed green. So those are the parent signal groups, 12, 14, 16, 18. It's like same here. But for the real like vehicle phase, I have 4 seconds of delayed green for them to account for LPI. And those are the TSP coding for all 6 movements. We do have like priority for some of the movements over the other ones. So after figuring all those out, I thought I had already overcome the biggest challenge for this project. However, then I hit this. When I tried to finally run the simulation, I got a warning saying, oh, we cannot run this ring gap area controller in this version of VISSIM. So I built this model in VISSIM 22. However, it has like 2 different RBC, the old one and the new one. The old one supports TSP, but the new one doesn't. You can only see that base timing and detectors under the new one. And that's why, like VISSIM 2022, like cannot run the RBC and got me that warning. And I also tried to use 2021 version. However, it just cannot read the newer version. So I was kind of, in this loop and out of options. And by the way, at that time, I didn't have many friends using VISSIM, but I do after this conference. So finally, I found a solution in the what's new in PTV VISSIM 22. So they acknowledge not all the features are supported, like preemption as well as TSP, but you can manually copy a file from the 21 installation file to the 22 folder. So I was able to get this beautiful model running for the existing conditions. See, we have one train stopping at the Tasman station and approach to the intersection. And finally got a green. So for traffic condition validation, we have some like previous studies using synchro and gave us the intersection delay. We compare that with the VISSIM delay. Although it's not apples to apples, but we get like fairly close results for the PM peak. And we also look into the volume change between the 2023 study and this study. Like for AM peak, we have an increase of 8%, and we also see increase in intersection delay. Unfortunately, we don't have like the same level of information for the other location, St. Carlos and Watts. However, we did some like visual inspection of the Q lens between the video observation and VISSIM result. They're also like within the same range. And for transit, we're talking about, like how can we measure transit delay at intersections? So we came up with two parameters. One is the chance of stopping. When we say stopping, it has nothing to do with the station. It's all about intersection and signal. And the other one is for those trains that stop at the intersection, what's the median stop delay for them? So those are the results for both locations. As you can see, in general, our result is better than the video observation, but that's primarily because of the additional stopping behavior we mentioned earlier, like stop at mid-block for higher priority trains, or stop to, like wait for the switch to happen, or like if you're ahead schedule waiting at the station, or like between the station and the intersection, something like that. And for San Carlos, we're pretty close, like only by 1% for chance of stopping, and for medium delay is almost the same. The client is pretty happy with our result. So moving to the future scenario testings, how would increased light rail frequency affect both transit and traffic delays? This is pretty straightforward for person testment. So we tested 4 different scenarios. Right now, we're running 15-minute halfway, and in the future, we may have this like 10-minute halfway for all the lines, or we cut the green line and now that green line running through this location and only keep like 2 trains here. So that's the same number of trains per hour. And another scenario, it's pretty aggressive to make, halfway for green line only 5 minutes with like 36 trains in total, or something in between 30 trains per hour. So this one maintain the same number of trains, but only 2 lines could, reduce the chance of stopping by about 8%, and medium stop delay like 2 to 8%. This is like for different lines, so we have a range. And for traffic delays, even better. For scenario 3, for example, we did see some occasional bunching for this direction, and both stop delay and vehicle traffic delay got increased by about 15 seconds. I'm going to run the animation, this one. And by the way, we created this light rail model in SketchUp. It's like very similar to the real world light rail over VTA, and import it to VISSIM. Another interesting fact is VISSIM, at least the 22 version, only supports SketchUp model below 2019 version. So I had to ask some other friend to help me do that conversion. And we did some additional testing to see what else we can do to improve light rail service. One is to add that missing advanced detector for eastbound orange line. And that alone can reduce stopping chance by up to 30% and cut stop delay by about 4 seconds for those are stopping at the intersection. And VTA is pretty bold about, like how they can do to improve service. One test we did is to eliminate all the vehicle left turns at this location. So this graphic is showing, what if we have only through movement and right turns at this location. Surprisingly, it's very good for traffic operations. We can reduce level service from E to C. However, for light rail, it's not that significant, like up to 7 seconds, and that's primarily due to the reduced cycle length. And then for San Carlos and Watts intersection, we tested 3 scenarios. Similarly, we can reduce from 15 to 10 for both lines, or like 10 for one line and 20 for the other, which keep almost the same number of trains per hour. Or like reduce halfway for blue line to 5 minutes. This is like matching the other location, and keep 15 for green line at this location. So yeah, overall, the scenario one is the best, and we can reduce chance of stopping by up to 10%. And for vehicular traffic, it's not that much. So the role of this study is to inform DB on which scenario to move forward with their service planning. So traffic delay here is only a reference. We did not really focus on traffic compared to light rail. Another simulation for San Carlos and Walls Way. It may look like 3 directions, but this one is only the service track, like this turn. Here. So we only have light rail running here through, and this one. This concludes my introduction for Silicon Valley. I thought this is the most challenging intersection in the world regarding light rail operation until I traveled to Europe and saw some other bizarre intersections in Switzerland. Like this one, you have 4 directions with, I think, more than 6 lines. And for the other location, is actually 2 intersections very close to each other in front of a train station. And all those lines fit into the light rail station in front of the train. So there's way to go. Thank you, everyone. Any questions? And also feel free to scan this QR code and add me as contact.